Okay, good morning, everybody. We're here on class 26 now. It's 11:09, so it's not quite time to get started. I did want to mention that I'm not going to be going over the midterm from last night during today's class. What I did is I just went through on a YouTube and wrote out the solutions very carefully and posted the video of me going through the solutions on the Quarkus. So if you go in the Quarkus and look down where you found the midterm and the team up questions, you'll see a video link to the solutions. And then also I've carefully written out the solutions with the rubric that I've given the markers so that you know where all the points are coming from specifically for those two questions. So why don't we get things rolling here? I'll show you what's on the agenda for today. I want to get into chapter 9 stuff. Share my screen. Okay, and make sure I've got my participants and chat and Q&A. Okay. Everybody's doing well this morning. Okay, so this is actually, it's not exactly, but it's a photo of the VLA, which is how Atkina opens chapter 9. And then there's a description of actually the discovery of the first radio telescope. Sorry, the first radio pulsar using a radio telescope made by Jocelyn Bell in, I think it was 1967 that she made this discovery. Which is a rotating star. So we're talking about rotating rigid bodies here, rotational kinematics, rotational inertia. So a neutron star that's rotating very, very quickly and sending out radio pulses is called a pulsar. And these were discovered, actually not with the VLA, these were discovered by Jocelyn Bell in Cambridge with her own actual radio telescope that they have at Cambridge. So it's just, I thought I would, I'm from an astronomy background, so I thought I'd clear that up. What's going on the MyLab and mastering? So I have posted a homework 9, chapter 9 stuff, which you can take a look at. There's also these videos and practice things, which you can check out. They're not for homework credit, but they're kind of funny. There's a video of this buzz cut guy spinning around, and he drops his bean bags. So that's a fun one. And there's also one on toilet paper, which I thought was really great. The question is a full roll of toilet paper versus an almost empty one. When you give it a small torque, which one spins up faster, I guess. And so this is about the rotational inertia of a roll of toilet paper. So that's a lot of fun. And so, two of you actually on the chat, just as we were coming in, asked a question about the homework credits and what's the maximum number of homework credits you can get. So this is actually from the course syllabus, talking about where all the marks are coming from. Of course, all the homeworks are technically optional, but as you accumulate homework credits, the weighting of your midterms and final assessments will be reduced from the 80% down to a minimum of 60%. And the breakdown of all the points that you can get, there's going to be 11 total Mastering Physics homeworks. We've already finished 8 of them. They're worth a total of 138 points. There are going to be 8 in-class Friday team-up group quizzes, each worth 15 points. So that totals up to 120. We've got a few more of those, including this Friday. There were 3 practice quizzes for the midterms. We've done all those. Those were 42 points. And then there's a couple others that Get to Know You survey and the LASSO pre-course diagnostic. That was worth 1 and 2. And then there's another one. So anyway, you total it all up, it comes to 305 points. So if you earn N homework credits, then X is equal to 20 times N over 305. And of course, you get all of those that you get, right? So I guess the one way of putting it is X is out of X. So it's 100%. All that X that you get is 100% on that. So So if you get less than 100% on either the midterms or the final assessment, then these homework credits just boost up your score a little bit. It's a little bit of a bonus. That's how that's working. And then the question I want to have for you, I'll launch a poll and then I'll look at your questions, is how did midterm 2 and midterm 4 compare? So this is just the fact. It is, for me, as long as we're in COVID, what I want is for you to do a couple of questions written out in a half an hour period synchronously, so all the entire class does them at the same time and then uploads it at the end of these 30 minutes. Now, I know that this is not easy, especially when the internet is not perfect, either from our end at U of T or from your end. And so I'm hoping we can try to, make it as smooth as possible. So one thing I did is midterm 2 was done on a Quarkus, submitted using that, I guess it's a assignment function on Quarkus. And then last night, we used CrowdMark. So my question for you is, how did they compare? So think about that, and I'll read these through for you. Let me just launch the polling. Was it A, they were equally good, you didn't have technical issues really, given my constraints at the top there, I'm gonna be doing this. I know it's not pleasant to do a simultaneous thing, but anyway, so B would be CrowdMark was a better experience for you than Quarkus for technical reasons. C would be CrowdMark was actually a worse experience for you based on these technical things. And then D would be that both CrowdMark and Quarkus were equally bad. You had major technical issues uploading your images for both. Or E would be you can't compare for some reason. And I think I might as well write down the answers here so we have a record of this. Percentages. I'm getting some interesting things in the chat as well. Thank you for that. I do save all these chats and I review them after class. So it's, okay, so let's finish up this poll. Maybe another 5 seconds to click in and answer, please. And I'll write down these percentages. I'll write down the numbers actually. So let's end the polling. Share the results. So what I'm seeing here is for A, which was the most popular answer, I got 155, which is 43% of the class. So that's good to know. 129 actually did have some issues with the Quarkus, I guess, and found that the CrowdMark was better. So that's also encouraging for me. But then, of course, there's the 68 who had the opposite experience. So that's unfortunate, 18%. But I think still there's sort of a winner there, I guess. And then 13 of you had a bad experience with both, and 4% couldn't compare. Okay, so that's helpful. Thank you for that. Let me just look at what's going on up here. Okay. Again, the chat window is a pretty good place to put your specific comments because I do save that. It goes under a text file. It's on my computer for all the chats that I have for all these classes. If you have specific issues, and then also specific issues are a good thing to email me, or we can chat about it in the office hour after this class or something like that. But Hugo, did you have anything general you wanted to mention before I get going?
No, this was mainly about the homework credits. What does it mean by 20n divided by 305?
That's X. So remember in the top, that's a really good question. So let me just quickly go back.
Yeah.
So the homework
right
credits are worth X% of the course, and X is some number between 0 and 20.
Yeah.
So if you didn't do any
Okay.
homework, then the homework credits are just worth 0, and they don't affect your mark. But if you got 305 homework credit points, then the homework credits are worth 20%, and you got the full 20%.
Oh, okay. So you have to get 305 to purely get 20.
You get 20 free credits. That 20 that would be your. You
Okay.
get 100% on that 20 if you got 305.
All right.
Okay.
Okay. Thank you so much.
Yeah, sure. That's a good question. And again, Eric, any general thoughts or questions before we get going?
Oh, I just wanted to ask, so the homework credits are for completion, not for what we actually get on the on mastering physics or on the quizzes.
No, that's not correct. It is for what you got correct. You have to get the answers correct, I think, except for there was that one practice quiz where I just gave everybody 16. But other than that, you have to get the answers correct to get the points, I think.
All right, thank you.
Sure. Both good questions. Thank you for that. Okay. It's also good to know that I'm not alone in the room, although I'm seeing lots of stuff on the chat. Okay. So let's get into some chapter 9 stuff, shall we? Suppose there's a horizontal disk, and this is how Kina kind of starts this chapter, and you're looking down on it from above. And so the rotation axis here, just like it was in chapter 8, is a dot. And what that dot means is that it's actually coming out of the page towards you. And in this case, the disk is rotating counterclockwise. So the direction of the velocity for each coin, if you put some coins on the table and watch them go around, they're little pennies here, they're always changing. Here's one, for example, if this is coin 1, then as it's rotating around, it changes its velocity continually. Okay. And then the other thing, which is interesting, is that the coins that are nearer to the edge of the disk are actually going faster than the ones near the center. Now, if you're right on the very axis of rotation, you're not moving at all. Your center is not moving. You're just rotating around. As you get further and further away from the axis of rotation, if you're on this table, then the coins are going to be moving faster and faster. And the reason for that is that they're sweeping out the same amount of angle in the same amount of time. So if they're farther, if the radius there is greater, then they go a farther distance in the same amount of time. So they're going faster. So this is talking about rotational kinematics. So you remember when we started studying motion, we talked about kinematics, which is just like velocity, acceleration, position, so how things move, description of how things move, versus dynamics, which is where we've got into forces, which is why things move, like Newton's laws and why they move. So we're starting here with rotational kinematics. How do things go when they're rotating? So during a particular time interval, all these coins went through the same angle. So we're going to use angles when we describe the motion of something that is rotating. That's the idea. So here is this rotational angular position. So if you set up a XY axis and you want to talk about some particles that are all on some object which is rotating, it's useful to set up a R variable, which is the distance from the particle from the origin, and a theta variable, I always call this theta, which is the angular position. So for any particle's position, you can specify its position with XY, or you can specify with R theta. This is called polar coordinates. So that's its angular position. And then this equation for arc length, S is arc length, works if you measure theta in radians. So for a lot of the equations for chapter 9, we're going to be using radians instead of degrees, so that we can use this fancy little equation, which is that the just R times the theta gives you the distance. And what's interesting is that there's 2 pi radians in a full circle, right, going all the way 360 degrees. So if theta is 2 pi, then the arc length is 2 pi r. and that's actually the circumference of a circle. So that's how it all works out. So that's angular position. Remember back with regular position, when we took the rate of change of it, or the slope of position versus time, we got velocity. So we're going to do the same kind of thing here with angle. We're going to do the rate of change of this angle, and you get velocity. And so one way of doing it is your delta theta divided by delta t, and the limit as delta t goes to 0. That's called the time derivative of theta. That's called angular velocity. And this Greek letter here is called omega. It's a lowercase omega. It's not a W. And so this actually comes up in mastering physics sometimes, is a lot of students call it a W and then they type W using the keyboard. And then the master in physics says, the answer does not depend on W, and it tells you you're wrong. What you have to do is actually click on the little Greek letters thing, keyboard, and find the Greek letter omega, or else you get it wrong. But what's interesting is that the final angular position equals the initial angular position plus this omega times delta t. So that's called uniform circular motion. Okay, we're pretty well. Let's do a little poll on this. Carnival has a Ferris wheel where some seats are located halfway between the center and the outside rim. Compared with seats on the outside rim, the inner cars have a smaller angular speed and greater tangential speed. And then you can kind of go through those. You're comparing tangential speed, which is the actual meters per second speed, versus the angular speed, which is that omega in radians per second. So you should see a new poll. You kind of picture it, the whole thing is rotating as one, and so different spots. This is the, you're comparing this one to an outer one. Okay. Do you know the 10 seconds to click in, please? Oh, backslash omega works. Interesting. Good to know. Thank you, Ulimo. All right, let's end this polling. See what people are saying. So 56% of you voted for C, and that's exactly the one that I was thinking of too. You're looking at the inner car. So they all cars sweep out equal angles in equal time. And what that means is that omega is the same for all. And that's the angular speed there. But obviously, if something's right at the very center, it's not moving at all, right? And so as you get farther and farther from the center, it's going faster and faster. I don't know if you've ever played that game where you link up your arms with a whole bunch of other kids in a line, and you try to go around in a circle, and the one person stands in the middle. I can't remember what it's called, but you're going around. If you're towards the edge of it, you're really flying, and you end up kind of, your feet go off the ground and you get injured and all kinds of stuff. So this V, the answer is that V is equal to omega times R, where R is the distance from axis. It gets bigger and bigger as you get farther away. So a pretty simple equation, really. Okay. It's on the next page here. Oh, you do that? Oh, nice. Okay. We have a figure skater in the class, so that's very cool. Does sound a little scary though. I've seen figure skaters do it. Okay. This is called rigid body rotation. So we've been talking about torques and things like that with where the axis of rotation doesn't matter where you put it because it's static equilibrium. Well, now we're going to talk about things where there actually is a literal axis and then things are rotating around that rotation axis. So now it's not arbitrary, it's a real thing. So angular velocity omega is the rate of change of angular position theta. So sort of analogous, right? This omega is to theta as the V was to X before. So you're sweeping out these different angles. The units of omega are radians per second because the units of theta were radians. And then there's this other thing. If the rotation is speeding up or slowing down, then it has angular acceleration, alpha. So that's not an A, that's an alpha. And you was saying that you can probably just type \alpha on mastering physics, and then it'll accept that. So that's a good tip, good pro tip. The units of alpha are radians per second squared. So, right. So I guess alpha is to this omega as A is to V. Right. It's the rate of change. Alpha is the rate of change of alpha of omega. So all points on a rigid body are going to have the same omega and also the same alpha. So here's an example of a wheel which starts rotating and then has positive angular acceleration, and then it slows down again. So, and we can actually, maybe I'll even turn off the let's see. Turn off the share screen just for a second. So if I don't stop the sharing, then I'm always this small thing on the YouTube video. But basically, what we've got is if you have a wheel like this, then we can set it up with, right now, let's see. Right now it's got positive displacement. So the angle is measured usually from the x-axis up, and that actually is the historical reason why you have positive being counterclockwise, because you tend to measure theta being measured away from x, right? So 90 degrees is here, 180 degrees is here. Actually, we should do it in radians, right? So pi over 2 radians is here, pi radians is there. I'm looking at the yellow one here. This is 3 pi over 2 or something, and then this is 2 pi, so go right all the way around. And so 2 pi is the same as 0. So what we're going to do is have an angular omega, which speeds up for a while and then slows down and then stops. So speeds up maybe fast and then slowly slows down. And that's what I've done on this graph here. Share again. Again, I got to get my chat window back up. My participants. Okay. Okay, so what I did is the angular velocity went up a little bit, up quickly, and then slowly went down again. And so I had positive angular acceleration alpha for a little while, and then negative, small negative angular acceleration until the thing stopped. So that's what that motion was there. And so what's interesting is that the arc length is s, which is theta times r. The tangential velocity is, we call it omega, or sorry, vt in meters per second. That's equal to omega times r. And then there's also something called tangential acceleration, AT, which is alpha times r. So this is not to be confused with the radial acceleration. Remember, so if we have this thing going around in a circle, let's look now at the orange thing. it's always accelerating towards the center, right? That's the radial acceleration. Well, if I'm speeding it up, like if I start slowly and then make it go faster and faster and faster and faster and faster and faster, then it's also got, it's speeding up, right? So it's got tangential acceleration. And that's what this alpha is all about. Alpha times r, tangential acceleration. So let's talk about a little bit about the rotational kinematics. The way it goes is that if something's rotating counterclockwise, then omega is positive. And if it's rotating clockwise, then omega is negative. And then the other thing is that if omega and alpha have the same sign, sort of like if v and acceleration have the same sign, then rotation is speeding up. And if they have opposite signs, then it's slowing down. Opposite signs, and rotation is slowing down. So that's how that works there. Yeah, we're going to have to skip those two. So just really quickly, I'm not going to do the poll, but we're going to say if this fan is speeding up, so this is right now clockwise. So what that means is omega is negative, okay? And if it's speeding up means that alpha is also negative. So this answer would have been D if I had done that, okay? So you can have negative alpha, but it's actually speeding up if omega is also negative. And here the fan blade is slowing down, but again, it's going counterclockwise. So omega here is positive, and it's slowing down. That means that alpha is going to be less than 0, right? If omega is greater than 0. So omega is positive and alpha is negative. That's what I was looking for there. Yeah, so omega kind of determines what the sign of alpha is. Omega is the easy one, right? Because it's just which way it's actually turning. And then alpha, if it shares a sign with omega, then it means speeding up. And if it's the opposite sign, it's slowing down. That's all. Oh yeah, there's a really good point there. So let me quickly look at this. Atang had a good question there. So this is sort of an analogy. We had in linear space, we had x specifies the position, unit is meters. Velocity is the slope of the x versus t graph, meters per second. And acceleration, a, is the slope of the v versus t graph, meters per second squared. So similarly, the rotational analogy here is that theta is angular position, measured in radians. Angular velocity omega is the slope of the theta versus t graph. So it's coming out in radians per second. And the angular acceleration alpha is the slope of the omega versus t graph. So it's coming out in radians per second squared. So this is all to do with trying to describe things which can actually rotate, okay, because it's important. A lot of things do rotate. And then Atang asked a question here on the chat window. Hello, Professor Harley. You said that the tangential velocity v comes from this equation vt is equal to omega times r. So the units we follow would be radians times meters per second. Why would this be velocity? Shouldn't the velocity units be meters per second? That is an excellent question. And in fact, the answer is right on this next slide, which is that radians are the magical unit. They just appear and disappear at will, okay? And so, example was exactly this thing. The units here, units check, exactly what Tang was saying, was that you've got omega is radians per second times r, which is in meters, obviously, the radius is in meters, is equal to radians times meters per second. But then what you do is you go like this, and it's equal to meters per second. So that's the trick. So basically, you can't do it with degrees, but you can do it with radians. It's a dimensionless unit, so that allows you to make it go away or come back. You just have to kind of use context to know whether the radians should be there or not. Okay. I think it is, if you leave the radians on there, if you say that the tangential velocity is 30 radian meters per second, that would be wrong, right? It doesn't make any sense. The tangential velocity is 30 meters per second. Sort of a weird thing. This is table 9.1 from page 256. It's showing you actually an analogy of equations. So these are the three kinematics equations that she had way back from, I don't know how many chapters, wasn't this chapter 2 or something, where there was V is V0 plus A. Well, there's an analogy. You just basically go to Greek. This is English letters. You just do the whole thing in Greek. Omega is equal to omega 0 plus alpha times t. The t stays the same. And then here's this 1/2 at squared. You got 1/2 alpha t squared. So you can do all this rotational kinematics by just taking these equations and converting them to Greek. I'm going to do a little example. A bicycle wheel has an initial angular velocity of, we'll call it omega 0, is equal to 1.5 radians per second. Okay, and we can kind of try to sketch it. And a constant angular acceleration of alpha is equal to plus 0.2 radians per second squared. Through what angle has the wheel turned between t equals 0 and 2.5 seconds? So you're trying to find this angle theta is equal to question mark. Okay. So so basically it's constant acceleration. So constant angular, I should say. So use equations from table 9.1. That's all really I have to say about that. There's not really a diagram for simplifying diagram, but basically let's use that the theta is equal to theta 0 plus omega 0 times t plus the 1/2 alpha t squared. That's the one I would use. And just set theta 0 equals 0. And so theta is equal to 0 plus 1.5 radians per second times the seconds, 2.5 seconds, plus 1/2 of 0.2 times the 2.5 squared. And plug all that in, and I got 4.37 radians. Okay. So this is, remember that 2 pi, which is around 6 radians, is the full circle. So this is a little bit less than that. It's more than halfway around, is less than that. Let's skip my evaluation step there. Good. Oh yeah, maybe. Well, I guess through what angle has the wheel turned between t equals 0? I would say that this is sort of an assumption to, at t equals 0, right? It's sort of stated right there. Just looking up at my chats here. Everybody's pretty happy, I guess. Theta 0 would be, I guess, the angular position when t equals 0. So I guess we just defined this. Sort of definition. Then I'll just quickly mention before we go on to rotational inertia, which is the last thing for today, is that this all relates back to something we've already done, which is the rolling without skidding, or I was calling it rolling without slipping constraints. So when you have a round object, which is on some surface, and it's rolling along, like I'm rolling this on my table here, then the distance that the axis, or the center of mass, travels is equal to the change in angular position times the radius of the wheel. So if the radius of the wheel is r, capital R, then the distance the object travels, actually I might as well call distance, is theta times r. The speed that the thing's going is v, is omega times r. We kind of did this before when I was telling you how to get something rolling without slipping. And then also the acceleration is alpha times r. And that's how a car works. If you're going to speed up your car, what you're doing is your engine is causing the tires to have some angular acceleration, alpha. And then the whole thing's rolling without slipping because of the static friction on the bottom of the wheels. And so that's your constraint. And that's causing the car to have acceleration, which has to be equal to alpha times r, the radius of your tires. That's how it works. Okay, so next thing is going to be rotational inertia. And I have this thingy here. So, but first let's look at my slide. Okay, rotational inertia depends on, so this is how easy something is to rotate. And this a little bit goes back to that toilet paper roll thing that was from your mastering physics video, which is that if you've got a lot of toilet paper on the roll, it's kind of hard for it to be rotated because it's got a lot of rotational inertia. So you can pull the toilet paper off and it just comes off easily. If you're almost at the end of the roll, then the rotational inertia is less, so it's easy to rotate, and so a little tug will cause the whole thing to rotate and spill all over the place. So it depends on the mass of the object, and also the distribution of the mass around the axis of rotation. So the greater the distance between the mass of an object and the axis of rotation, the greater the rotational inertia. Okay, and my demo here is just showing, Pi has brought this nice little thing that's on actually, can we lower it? Put it center of the screen here. It's showing two adjustable masses that are on this little plastic rod. So right now it's got the maximum rotational inertia. So if I push it with a small little force here, it accelerates more and more and more and more and more. This is sort of a constant torque. I'm speeding it up more and more. And if I want to slow it down, I have to kind of put a lot of force on it. I can keep the same mass, but really reduce the rotational inertia by putting these things at the center. Now, if I push it, it really, really easily speeds up. And then it easily slows down again. Even a small little force will stop the thing. You can imagine it's easier if you're actually doing but then if you increase it again, take the same mass, put it way out here. I do that again. It takes me a while to get it rotating. Okay, but I can get it rotating that fast, and then ow! It wants to keep rotating. It has more rotational inertia. So this is like the rotational analogy of mass. So remember, in linear, if you have something that's more massive, like a big locomotive train, it's harder to accelerate it, and it's also harder to slow it down. Right? Because it's got so much mass, it wants to keep its constant velocity. Well, this wants to keep, it's got a lot of rotational inertia, so it wants to keep its angular velocity. It's hard to change its angular velocity. You have to put in a lot of torque to change its omega, right? But if you reduce it, and all of a sudden it just twirls very easily because this is a plastic rod and these are now near the center. So you've reduced that rotational inertia. Maybe I should have turned off the share there. But so, and there's an equation for it. So if you have a body made of n particles, each of mass m sub I, where I is going from 1 to capital N, and each particle is located at a distance r sub I from the axis of rotation, then for this body, we have rotational inertia, I, which is equal to m1 times r1 squared plus m2 times r2 squared plus m3. So all the little particles, you take their mass times the square of their distance from the rotation axis and sum it all up. This is the sum from I equals 1 to capital N of all the m sub i's times the r sub I squareds. The units of rotational inertia are kilograms times meters squared. The meters squared is coming from that distance from the axis. And so in order to define what is the rotational inertia, you have to first specify or figure out what the axis of rotation is. So let's do a little example here, a poll. Which of these two dumbbells has the larger rotational inertia about the midpoint of the rod? So the rotation axis is the midpoint. So I can draw. That's where you're going to measure R from. Remember that I is equal to the sum of all the m times r squareds. It says here the connecting rod is mass or negligible mass, like a plastic rod or something. Should we do it? I'm going to end the polling and see what you guys got. Maybe use your intuition here, or 5 seconds. That's what you guys got here. I see 61% are voting for dumbbell B. Let's take a look at this. I think that might be right because I think it matters more. It's got half the mass, but twice the distance. And it seems like since the R is squared, probably the distance matters more than the mass, but we can quickly just figure it out, right? It's going to be, there's two of them that are identical. So it's 2 times the rotational inertia of one of them. So that's going to be m times r over 2 is the distance from the center, all squared. So what I got there is you got 1/2 times m times r squared, because there's a 2 over 4. And then IB, again, it's going to be 2 of them. M over 2 is their mass times their distance from the axis, which is r, all squared. And so you got 2 over 2. This is just m times r squared. So IB is actually twice as much as IA. So very good. Do a couple more examples. We move on. So we have 4 small metal spheres, each with mass 0.2 kilograms, are arranged in a square that's 0.4 meters on a side and connected by extremely light rods. So we can kind of put them here. This is M, 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 and M equals 0.2 kilograms. This distance here, we're going to call that, maybe we can call it x or something like that, is 0.4. Find the rotational inertia of the whole thing, and the rotation axis is through the center like that. Okay. It's through the center of the square perpendicular to the plane of the square. So what I'm going to do, let's call them 1 and 2, and I'm not drawing it very well, and 3 and 4. If we have all of them, then this distance, we need this distance, where if this right here is x over 2, I think, and here's a right angle here, and that this also, I think, is x over 2 from here to here, then this would be R2, this is R1, etc. They're all going to be the same. So R1 equals R2 equals R3 equals R4. Let's call that R. So, and I think you can use Pythagoras or something, but basically I is going to be M1 times R1 squared plus M2 times R2 squared plus etc. It's going to be 4 times M times R squared. Okay. And then let's just use Pythagoras to actually find this. I think that R squared is going to be equal to x over 2 squared plus x over 2 squared. So R is equal to the square root of 0.08. Oops. Yeah, well, whatever, 0.4 squared times 2. Okay, and I got that actually square root of 0.08. So what you've got is I is equal to 4 times 0.2 times 0.08, square of the square root, and I got 0.064 kilograms meters squared. And then similarly, what we can do is change the axis of rotation. So if you now do the rotational inertia of an axis through the center of the square, parallel to its plane instead of perpendicular to the plane, then what we get is, in this case, if this is 1, and this is 2, and 3, and 4, they're all this distance, R is equal to x over 2. Okay. It's the same sort of thing. I is equal to 4 times m times r squared. It's equal to 4 now times 0.2 times 0.2 squared. So 0.2 kilograms times 0.2. You get 0.032 kilograms meters squared. And that is actually about half of the I for rotation axis perpendicular to the plane. So if we go backwards one slide, we had 0.064 kilograms meter per second when the axis was going through the object, and when you put it sideways, then it decreases by half. It depends where your rotation axis is and what the shape of your object is. Here's some pictures from the book. If you have a thin hollow cylinder of mass m and radius capital R rotating about its axis, then the rotational inertia is m times r squared. If you have a thin rod rotating around its center, kind of like this one is, it's 1/12 of the mass of the rod times L squared. But if you rotate it around its end somehow, I can't do it with that one, then it's 1/3 ml squared, so it's bigger. If you have a solid disk that's filled in the middle, you get 1/2 mr squared. If you have a solid sphere, it turns out to be 2/5 the mass of the sphere times r squared. If you have a hollow sphere like a ping pong ball, you get a different equation. It's 2/3 mr squared for, again, rotating around its center. Yeah, so rotational inertia I, actually, I do want to ask you guys this one. Who knows the answer to this one? Before we split here. This is my last slide, I think. What is rotational inertia the rotational analog of? Is it kinetic energy? Is it mass? Is it momentum? Or is it the tendency of anything that is rotating to continue rotating? What's the analogy to a linear that we had before? Oh boy. Okay, I'm gonna just show you guys what happened here. This didn't go so well. So yeah, I'm not looking for this. Whoops. Definitely not looking for that. I mean, it is true that things that are rotating, it's the rotational analog of mass. If you answered B, you're among the 15% who are 42 of you. That's exactly what I was getting at here. And so the idea is that we had all these kinematics analogies. There's now going to be dynamics analogies. That's what we're going to be doing on Friday. So the analogy of force is torque. The analogy of mass is rotational inertia I. And the analogy of Newton's second law is that alpha is the torque divided by I. So that's all the stuff. You can read ahead a little bit. Chapter 9.3 on Newton's second law for rotation and 9.4 on rotational momentum. Don't forget that on Friday, we're going to have a group team up quiz worth 15 points for which I would like you to work in a group of 3 or 4 students. Hopefully your practical pod can make a call on your Microsoft Teams and you can get together there, chat about it. We'll give you 10 minutes to work on that thing together and then talk about it in class. Okay. So I hope to see you then. And thanks very much. And I'm going to stay on this call for, I'm going to turn off the record, but then I'm going to stay on this call for another half an hour and see if anybody has any questions.